All right, so last time we were talking about classifying, how to classify what your stability looks like based on your eigenvalues. And we kind of talked about all the things except for the very last one. So I feel like I should, well, actually the very last two. So just to kind of actually, there. I have so many things in here. Sorry, I just wanted to show you. Remind me of the last time. Yeah, so last time, briefly, we had said if both the eigenvalues are positive, then you have a source, aka a unstable node. If both the eigenvalues are negative, you have a sink, aka a stable node. And if one's positive and one's negative, you have a saddle, which I actually did right there. And also just a saddle is considered an unstable system. And then we also talked about or mentioned how if you have complex eigenvalues, if the real part is positive, you have an unstable spiral. And then I was going to say, but ran out of time, but now we're going to say that if, on the other hand, so if your real part, if when you have lambda equal to, keep hoping it'll be good. So if your lambda is this complex number, if A is less than 0, then we have a stable spiral. So in other words, an inward spiral. So it's going to look something, like where you keep getting closer and closer to the origin. We'll talk a little bit later about how to determine the direction of the spiral. It's not like super important, but it is something that's not too hard to figure out once you figure out it's a spiral. And this kind of goes along with the same thing, right? Our solutions look like, so we're saying our solutions look like some C1e to the A plus or minus BIT times V1 plus C2e to the A plus or minus BIT times V2. And again, if A is negative, then these are going to be getting smaller and smaller and smaller. And really, again, the way we look at this, right? If we look at this part here, this E to the A plus or minus BI, I guess it should just be plus really, but it's okay. This is looking like E to the AT times E to the either positive or negative BIT. And then this part here becomes the cosine of plus or minus BT plus I sine of plus or minus BT. And so if A is negative, this part's going to get smaller and smaller and smaller and smaller. And this part's just going to make it oscillate, which is giving us the spiral shape. Finally, the last thing, actually, if on the other hand, A is equal to 0, meaning your eigenvalues are purely imaginary. Then we have what we call a center, meaning it's just going to circle back around on itself. It's not going to oscillate, or, well, it's going to oscillate, but the values aren't going to get larger or bigger, because essentially what's happening is in this situation here, we just have E to the BIT. And so when you write it this way, you're just getting C1 times cosine of BT plus I sine of BT plus the rest. But it's not getting bigger or smaller. I mean, it's getting bigger or smaller, but it's not like it's growing infinitely large or shrinking down to being 0. It's just going back and forth. And this pattern here just cycles back on itself. So every time you go through, essentially every time this BT value goes from 0 to 2 pi, you're getting one full cycle of the sine cosine function. You're just getting back to where you started. So this is going to look something like this, where you have just this kind of thing. And you do really actually end up back on yourself, which is kind of interesting. So those are the 6 things that can happen. And it's all, if you're trying to classify what kind of thing happens, all you need to know is what the eigenvalues are. That's it, which is kind of great. So for example, examples here. if we said, oh yeah, of course, yeah. Go ahead and just, so for example, if we said, if we have the usual dx dt equal to a times x, we want to analyze the stability of the equilibrium. Of course, the equilibrium is the point 0, 0. So the question we're asking is the equilibrium a sink, a source, a saddle, a stable spiral, an unstable spiral, or a center? I never liked the word center, but that's what they call it. That's what the last one was. That's what you call, when it just loops around like that, you call it a center. So let's look at this first one. Let's say our matrix was -4, 2, -5, 3. So there are a couple different ways you can approach this. One way is just to find the eigenvalues. So we can find the determinant of A minus lambda I. It's going to be equal to -4 minus lambda, 2, -5, 3 minus lambda. And then that's going to equal, I always forget to write the determinant part here. It's the determinant of that matrix, which is then going to be -4 minus lambda times 3 minus lambda minus 2 times -5, which is equal to, let's see, we've got lambda squared plus 4 lambda minus 3 lambda gives me a plus lambda, minus 12 plus 10 is minus 2. And that does factor. It factors as lambda plus 2 times lambda minus 1. So what do we have? Well, we have a negative eigenvalue and the positive eigenvalue, so we must have a, starts with an S. You're like a lot of them do, right? Yeah, it's a saddle. Now, I will point out, you could have also figured it out as a saddle just by taking the determinant of this matrix. So the determinant of A is -12 minus -10, which is -2. But we know, because we've been told, now you can actually show pretty easily, but I would just encourage you just to believe that the determinant is equal to the product of the eigenvalues. Well, if the product is negative, one had to be positive, one had to be negative.
That's how I did the homework from like,
yeah,
like
totally valid. Now, if the determinant had been positive, then I would go look at the trace, because if the determinant's positive, you don't actually know if it's really, this is really kind of only great if the determinant's negative. If the determinant's positive, it's kind of like, well, okay, there's a little more to do, but we can talk about that too. So let's look at another one. Let's say our matrix was -3, -1, 1, -6. And let's go ahead and actually go in the other direction first. So let's talk about how the determinant is equal to -3 minus 6 times -6, which is 18, minus 1 times -1, which is going to be 19. So our determinant's positive. Our trace is -3 plus -6, which is -9. So here's what I know so far based on these two things. It's a stable system, but I don't know if it's a stable node or a stable spiral. But I can figure it out really easily, because if I think about what my eigenvalues should be, well, there's this whole formula using the trace and the determinant, right? The eigenvalues are equal to the trace plus or minus the square root of the trace squared minus 4 times the determinant over 2. So I already know it's stable. I know it's not a saddle, right? I mean, you could have said, James, of course we know it's not a saddle. You just said it was stable. right? But the determinant is positive, so it's not a saddle. The trace is negative, so we know it's stable. And then to determine whether or not it's a spiral or a node, we just have to look at this discriminant here. Is that part there going to be positive or negative? Well, let's check it out. The trace squared minus 4 times the determinant is going to be -9 squared minus 4 times 19, which is going to be 81 minus something that's a little bit less than 80, right? 4 times 20 is 80, so 4 times 19 is 76. That's positive, which means this number is real, which means we have a stable node. The word's always, or a sink, if you want to call it that. Now, you could have, I should point out, you could have just found the eigenvalues, right? You could have said, James, I don't want to do that, or I don't want to do this. I just want to be like, what are actually the eigenvalues? They're going to be the trace, which we just said was -9 plus or minus the square root of the trace squared minus 4 times the determinant all over 2. So that ended up being -9 plus or minus the square root of 5 all over 2. My eigenvalues are real. For sure, one of them is negative, because -9 minus the square root of 5 is definitely negative. Is the other one also negative? Yeah, because -9 plus root 5 is still a negative number. So they're real, they're both negative, that means it's a stable node. Either way is fine, it just kind of depends on what you feel most comfortable with. And of course, right, I didn't even do it either one of the kind of normal ways, right? I didn't actually find the eigenvalues in the way we typically do by doing the determinant of A minus lambda I. This one, you could have done it that way too. You're going to end up with the same thing that we got here though, right? Because you're going to end up with the equation, right? If you had done it the other way, your determinant of A minus lambda I is going to end up giving you lambda squared minus the trace times lambda plus the determinant. Sorry, where'd you go? Determinant? Yeah, 19. Which is going to exactly get you back to this same solution. So really, it's like the hard part about this section is there's kind of like so many different ways you can do the same thing. It's like, how do you decide which way to do it? And the way you decide is what works best for you. But I suppose someone might just give you like a trace and the determinant, be like, hey, here's the trace, here's the determinant. What do you know about the solution or the equilibrium? Okay, let's do, so where'd you go? Other examples. So I wanted to talk a little bit about the complex eigenvector situation, because he's definitely talked about that in class, and there's definitely at least one homework problem where you have to actually find the general solution that has complex eigenvectors. And it's kind of a big pain in the butt. So let's look at, let's look at this example. So let's say, well, first of all, let's say we have this matrix again. So actually, let's ask the same question we were just asking. Here's our matrix: -1, -1, 5, -3. And I want to classify the solution, the equilibrium. Sorry, I keep saying solution, meaning. So classify the equilibrium. And we're going to do all the other things as well. So we might as well find the eigenvalues in kind of the usual way. So determinant of A minus lambda I is going to be -1 minus lambda, -1, -3 minus lambda. And multiplying that out, I've got -1 minus lambda times -3 minus lambda minus -1 times 5. That's going to give me, let's see, lambda squared plus 3 lambda plus lambda is plus 4 lambda plus 3 plus 5. So there's my quadratic equation. And that definitely doesn't factor. And if we start looking at our solutions, we're going to get lambda equal to -4 plus or minus the square root of, 4 squared minus 4 times 8 all over 2, which is going to give us -4 plus or minus the square root of 16 minus 32 is -16 all over 2. And I would simplify this. I'm going to write this as -4 plus or minus the square root of -16 is 4i, and then divided by 2. So that's going to give me a -2 plus or minus 2i. So we know for sure that the equilibrium is a stable spiral. Stable because the real part of the eigenvalue is negative, spiral because it is a complex eigenvalue. So yeah. What else do I want to say about this before we get going here? No, not a whole lot. So if we want to find the general solution, I would strongly encourage, now, and he said, I think he said in class, you don't have to memorize this formula. He'll definitely give it to you if he asks you questions about it on a test. But I would encourage you to not memorize this formula, but to look in the book. So this is in section 10.2. I believe it's formula 13. It's on page, yeah, page 647. And it's formula 13. So the general solution is the following. Actually, I'm gonna back up just one second. Let me do one more thing before we start finding the general solution. Let's find an eigenvector. So typically, what we usually kind of default to is using the eigenvalue where you have a plus the imaginary part, because it's just a little easier and it doesn't actually matter which one you choose. So let's look at lambda 1 equal to -2 plus 2i. And we're going to find the eigenvector for it. So we're going to do the usual thing. We're going to say that so we're going to do the usual thing, but maybe in the less usual for James way, meaning I'm not going to do this, even though it would work just fine. Instead of doing it that way, which is my usual preference, we're going to instead do it the way where you do A minus lambda times the identity matrix times your eigenvector is equal to the 0 vector. This is generally the better way of going if your eigenvalue is not pretty looking, meaning it's either complex or it has some irrational parts in it. So let's do it. We're going to have A minus lambda I. So we're going to do, let's see, -1 minus -2 plus 2i, -1, 5, -3 minus -2 plus 2i. Times our eigenvector that we're trying to find equal to our equal to the 0 vector. Now, you can take either equation, but usually you're going to want to take the one where you get to let x equal 1. So I'm going to take this first equation here because here's what I'm going to get. And let's simplify this just a tiny bit. Or my pens. So let's say -1 minus -2 is going to be a +1 minus 2i. And if I were going to simplify this, this would be a -3 plus 2. So this would be a -1 minus 2i. So looking at the first equation, I'm going to have a 1 minus 2i times x minus 1 times y equal to 0. Solving for y, I get y equal to 1 minus 2i times x. So I'm going to let x equal 1 and y equal 1 minus 2i. So my eigenvector is going to be the vector 1 minus 2i, which we want to write as a real vector plus an imaginary vector, meaning I'm going to break apart the real pieces and the imaginary pieces. Sorry, I've got a million pieces of paper as usual. One thing I'm not sure about going. You're not. No, I know where it is. I know where I hid it from myself. Nope, I really don't. Okay, it's fine. Just want to make sure I'm not making a mistake. Okay, so this is what we're going to call our, if we're looking at equation 13, this is our U plus our I times W. So I should really write this as 1, 1 plus I times 0, -2. And that's my U plus my I times W. Okay. So then if you have your U and your W and your A and your B, then here's the general solution. I'm literally just copying this formula from the book or from his notes. The general solution is x of t equal to, it's kind of gross and long, k1e to the at times u cosine of bt minus w sine of bt plus k2 e to the at times w cosine of bt plus u sine of bt. No one should memorize that. It's terrible. Really want something. Find it. It's not showing up. Oh. I think I could be a little more organized. Usually I am. No, I'm looking for this. I have, like, I was working this problem before. I just wanted to check that I didn't make some stupid mistake. Oh no, you know what? Sorry, I didn't actually bring that up. So once you have U and W and A and B, you just have to throw it all into this formula. Now it's going to be kind of gross. So let's give ourselves a little bit of room. So we're going to say, all right, our general solution is going to be K1 e to the, so our A is -2 times U, which is the vector 1, 1 times cosine of BT. B is +2, so it'd be cosine of 2t minus W, which is the vector 0, -2 times sine of BT. B is still 2 plus K2 e to the -2t times W, which is 0, -2 cosine of 2t plus U times sine of 2t. And then people typically kind of write this in a more compressed form. We can write this as K1 e to the -2t times the vector. So this first vector is 1 times cosine of 2t minus 0. And then the second component is cosine of 2t minus -2, so plus 2 times sine of 2t. Plus K2 e to the -2t times 0 times cosine of 2t plus 1 times sine of 2t. And then the second component is -2 cosine of 2t plus sine of 2t. And there's your general solution in all of its glory. Questions, comments, observations? No complaints? It's not so horrible. I mean, if you don't have to memorize it. If you had to memorize it, but really, so your job really, if you're asked to do a question like this, is as typical, find the eigenvalues. They're going to be imaginary. Identify your A and your B, and then find one of the eigenvectors. It doesn't matter which one. And then identify the real part of the eigenvector and the imaginary part of the eigenvector. Those are your U and your W. And then just throw them into this formula. Let's do one more just for practice, because there is one more thing I want to do. I do actually need something in my head. Oh, it's right here. It's right in front of me. Okay. Oh, no, that's fine. Let's do this. So let's say we had, yeah, sure. So another one. So let's say, and this is actually, this, well, not doesn't matter. So let's say we have this matrix, A equal to -1, 2, -3, -1. And we're also given an initial condition that x naught is equal to the vector 2, 0. So what does this mean? This means that we have to solve for K1 and K2. Or if it's a situation where you have real eigenvalues and eigenvectors, you solve for C1 and C2. I don't know why we call them K1 and K2 when it's imaginary, but we do. So we do. If you called them C1 and C2, it would be totally fine. So let's, in fact, why don't, yeah, I think it's good practice. You both should find the eigenvalues. I'll let you define the eigenvalues. I'm going to start doing it, but I'm going to go really slow. So here's what I'm getting. I didn't actually get my eigenvalues yet. I got to this quadratic equation, lambda squared plus 2 lambda plus 7 equals 0. I also then wrote it the other way. The determinant 7, the trace is -2. So you could also say it's the trace plus or minus the trace squared minus 4 times the determinant all over 2, which is the same thing you would get if you use the quadratic formula here. Either way, we're going to get lambda equal to -2 plus or minus the square root of 4 minus 28 is -24 all over 2. Which it is in our best interest to simplify this if we can. So I'm going to write this as -2 plus or minus 24 does have a factor that's square. It's 4 times 6. So I can think of this as the square root of 4 times -6 all over 2. And the square root of 4 is 2. So it's -2 plus or minus 2 root -6 over 2. And that's -2. Sorry. Well, it's really -2 divided by 2 plus or minus 2 divided by 2 times the square root of -6, or preferably -1 plus or minus I root 6. There are other ways to get there. That's the way I probably see it best. Okay, so I just want to remind you at this stage, you totally should know what kind of equilibrium we have. Let me ask you first, is it a node or is it a spiral? Well, the eigenvalues are real, it's a node. The eigenvalues are imaginary, it's a spiral. This one's definitely imaginary, so it's a spiral. Okay, now if we look at the real part, we should be able to tell if it's stable or unstable. This real part is negative, meaning it's going to be stable. Because negativity is associated with the exponent getting smaller and smaller and smaller. So this is a stable spiral again. Oh, I was going to talk about how to see if it's which direction it goes, but we'll go back to that. We'll do that at the end here. Okay, so let's find the general and the particular solution. So to do that, we need an eigenvector. And again, you can pick either one, but it's again fairly standard to use the one where you're adding the imaginary part. So let's look at lambda equal to -1 plus I6. Just because it's easier to deal with something that's plus versus something that's minus. So we're going to go back to our matrix, which I just totally forgot what it was. So here's our determinant, not determinant, we're just doing a minus lambda I. So a minus lambda I times our eigenvector should equal 0. So a is -1, 2, -3, -1. So it's going to be -1 minus -1 plus I root 6, and then 2, then -3, and then also -1 minus -1 plus I root 6 times our eigenvector equal to 0, 0. I'm going to simplify this. -1 minus -1 is just 0. So this is just negative I root 6. And so is this. You can pick either one. So I just want to point out either way of doing this is fine. Meaning you could either say negative I root 6 plus, times x plus 2y is equal to 0. And then you would get 2y equal to I root 6x. And I wouldn't divide both sides by 2. I would just say my eigenvector is going to be xy equal to x is the coefficient of y is the coefficient of x. That's the way I would do it. Alternatively, you could use the bottom equation. It's going to look different, but I promise you it's going to be exactly the same. So if I did it this other way, I have -3 times x minus I root 6 times y equal to 0. And if I do the same thing, I'm going to have negative I root 6 y equal to 3x. So here my eigenvector is, let's see, x is negative I root 6, and then y is positive 3. And I know those really don't look the same. And I guess I lied a little bit. They're not actually the same, but they definitely are multiples of each other. So the way you can see that they're multiples of each other is if we multiply this first one. This is not super important, but it is worth knowing. If you multiply this first one by I root 6 over 2. How do I know, negative I root 6 over 2. How do I know that's what I'm going to choose? Because I'm trying to make this one equal to that one. So I'm going to multiply 2 by negative I root 6 over 2. Oops. Sorry, times negative I root 6 over 2. Let's see what happens. Well, obviously 2 times negative I root 6 over 2 is going to give you a negative I root 6. Now check out the bottom part. What's root 6 times root 6? 6. Divided by 2 is 3. And then I times negative I is negative I squared, which is negative 1, which is 1. So this bottom part here really is 3. So they're both multiples of each other, which makes sense because they are both eigenvectors. So either one is a valid choice. So I just wanted to reassure you that you can use either equation and it's going to work out just fine. So if one of them looks particularly easier than the other one, I would say use that one. All right, so now we've got all the pieces. Well, almost. We should do one more thing. So actually, we should do 2 more things. So first of all, I should point out, we found for this eigenvalue, this eigenvector. Oops, that's a 6. And then you should know, or I suppose I should let you know, that once you have one eigenvalue and one eigenvector, you have both. Because we know the other eigenvalue is -1 minus I root 6. And the other eigenvector would be positive I root 6, 3. So the nice thing about these complex eigenvalues and eigenvectors is that once you know one of the eigenvector pairs, the other one is just the complex conjugate. So every imaginary part just changes sign. It's kind of great. So the other thing we need to know is that V is equal to, well, let's see, I've got 0, 3 is the real part, plus I times root 6, 0 is the imaginary part. And this is my U, and this is my W. Then, just like before, we throw the formula at it, right? There is some small analysis you really can do if you want to, but I don't think it's worth your time. I think you should just be like, okay, there's that, and then, okay, in the book, equation 13, x of t is equal to k1 e to the, oh, I also should write down what a is, right? A is -1, b is positive root 6. Okay, so here's my formula. I do feel like I should write that again, even though it's kind of a pain. U cosine of bt minus w sine of bt, and then plus k2 e to the at, and then it's w cosine of bt plus u sine of bt. If you do it enough, you'll memorize it. Not that you should, but I'm already starting to be like, oh, I kind of remember what the formula is. So do something enough times, you can memorize it. You just probably don't need to. All right, and then I just literally turned on the page I need, so then we're just going to be like, all right, x of t, my solution is k1 e to the -t times u, which is 0.3 cosine of root 6t minus w, which is root 6.0 times sine of root 6t plus k2 e to the -t times w, which is this one, times cosine of root 6t plus u, which is the other one, times sine of root 6t. And then we throw it all together, meaning I've got k1 e to the -t. This first vector is kind of nice in that there's zeros in the other spots, so it actually kind of isn't too terrible. It's just going to be the top component is going to be negative root 6 sine of root 6t, and the bottom component is going to be 3 cosine of root 6t. And then the second part is going to be k2 e to the -t. And then the first component is going to be root 6 cosine of root 6t. The second part is going to be 3 sine of root 6t. Oh, interesting. Okay. So yeah, that's fine. There's something. So okay, two things. One, the solutions I'm looking at, this was the eigenvector I meant to use, but it's okay to use either one, right? This one and this one are actually the same. Well, this one and this one are the same. I feel bad. I keep making small little errors. I'm just like, rough. I did make a tiny error, but we can fix it. My eigenvector actually had a negative I root 6 there. So really that should be a negative root 6 there. So our b value should actually be negative root 6. That's a lot of negatives. Sorry about that. Carried away. So that should actually end up being then a positive root 6 there, negative there, negative there, there, negative there. Sorry, I didn't mean to do that. It's definitely not my intention. The other thing we wanted to do was we want to find the K1 and K2. So we were given the x naught was equal to the vector, I believe it was 2, 0. Somewhere, yeah, 2, 0. So then we're going to set t equal to 0, and we're going to get 2, 0 equal to K1 root 6 sine of well, what sine of 0? That's cosine of 0. Yeah. And then cosine of 0 is going to be 1 plus K2 times e to the 0 times negative root 6 times cosine of 0 is 1. And 3 times sine of, oh yeah, of course, I'm sorry. Always. So we end up getting that 2, 0 is equal to K1 times 0, 3 plus K2 times negative root 6, 0. And it's very, very not too terrible to solve for K1 and K2. It looks like K1 is going to be 0 and K2 is going to be 2 divided by negative root 6. Yeah. So then our particular solution is going to be 2 over negative root 6 times e to the negative t times negative root 6 cosine of negative root 6t 3 sine of negative root 6t, because the other part was 0. So these imaginary eigenvector ones are kind of a mess, right? Like there's a lot of little pieces going on here. And like I've demonstrated, you need to be extra careful because it's easy to miss a negative sign somewhere. I know there's at least one homework problem where you actually have to do this. I think it's section 10.3, number 1. Pretty sure. And I will tell you, the eigenvalues you get are not very nice. They are very, like, I think it's like you get like your eigenvalues are like plus or point like 0.005 plus or minus 0.001 or something. It's it's very finicky. So just take your time with that problem, go slow, and be careful with your eigenvalues. I would also mention the answer to that question is in the back of the book. So you can always check your answers as well. But just be careful with that one because it is a little gross. Let's see. Oh, 156. All right. Is there anything else? Oh yeah, I know what I was gonna say. So let's talk briefly about just, so I'm gonna go back a little bit because I wanted to mention how you can figure out what direction the spiral is going. Let's actually do that for both of these. So that one, sorry. So this one here, we definitely had a saddle and we found our solution. Well, in fact, so here was our, right, here are our eigenvalues. Whoops. Here are eigenvalues that told us we had a solution. So let's go actually revisit this one for just a second and say the following. So we saw before that this matrix, -1, -1, 5, -3, had eigenvalues that were -2 plus or minus 2i, which told us that it was a stable spiral. Okay, but what direction is the spiral going? Well, to answer that question, what you really want to do is just draw a couple arrows in your phase plane, meaning if I think about what these equations actually mean, right, this is dx1 dt equal to -1 x1 minus 1 x2, and dx2 dt equal to 5x1 minus 3x2. You can pick a couple points. We know it's a spiral. We know it's spiraling inward. All we really need to know is if it's going counterclockwise or clockwise. Now, I will tell you, if you know something's a spiral, you can look at one of these off diagonal corners and know which direction it's going, whether or not one's positive or negative. I don't remember what it is. I literally have it like written on a post-it on my computer. Like, oh, if this one's positive, it goes that way. But really, that's not very scientific. You're just kind of like looking at things. Whereas we can just find it by picking a couple points. Like if I pick the point, say x1 equal to 1 and x2 equal to 0, well, let's look what I get. If x1 equals 1 and x2 equals 0, dx1 dt is going to be -1. And dx2 dt is going to be +5. So what I see there is that at the point 1, 0, I'm going 1 left and 5 up. So I'm going that way. And really at that point, I'm pretty sure I'm going counterclockwise. Right? Like it'd be hard to imagine somehow turning around that way and going clockwise with the spiral. But we could test another point. Let's test x1 equal to 0 and x2 equal to 1. So over here, by plugging in those values, I'm going to get dx1 dt equal to -1 and dx2 dt equal to -3. So now I'm going left and down. 1 left, 3 down. So more down than left. Yeah, that's looking pretty counterclockwise. So I'm pretty sure that my spiral is doing something like this. I'm going to try and hit these points right like that. And we're spiraling inward. So that's the way I would encourage you to think about how if you have to find the direction of the spiral, that's how you should do it, by just graphing a couple direction arrows and seeing which way it's going. I'm curious about our other example. I just want to see one thing here. Yeah, cool. So I'm pretty sure, although I'm not 100% sure, that this other matrix should be spiraling the other direction. And the reason I'm pretty sure is because these matrices have off diagonal elements that are opposite signs. So this one's positive, whereas this one's negative. This one's positive, whereas this one's negative. So I'm pretty sure you could say, well, I know if it's a negative up here, it's counterclockwise, and if it's a positive up here, it's clockwise. I want to caution you, you can only say that if you know it's a spiral. Right? If it's a node, that's not that. But let's look at the other one real quick just to see. So the other one, the matrix was this. The matrix was -1, 2, -3, -1, and the solutions, the eigenvalues were, what were they? -1 plus or minus I√6. So again, we know we had a stable spiral. And if we just check out a couple points here, so again, if I plug in 1, 0, so I plug in 1, 0, dx1 dt, right? If I'm thinking about multiplying by x1 and x2, dx1 dt is going to be -1 plus 0. And dxy dt is going to be -3. Sorry, dx2 dt is going to be -3. So I'm going left and up. Sorry, left and down, apologies. So at this point here, I'm going left and down, and more down than left. So I'm pretty confident I'm going to have clockwise spiraling here. Let's look at one more point. 0, 1. If I can 0, 1, dx1 dt is going to be 2. And I should let you go. And dx2 dt is going to be -3, 0, -2, 1. -1. So at this point here, I'm going right and down. Yeah, I'm pretty convinced if I'm spiraling, I couldn't be spiraling clockwise, or sorry, counterclockwise. I'd have to be spiraling in this sort of way. So it's usually pretty easy to check if your spiral is clockwise or counterclockwise. You can often get it by just plugging in 1 point. Usually, if you plug in like 1, 0, 0, 1, unless it's pointing like, if it's pointing out to the right at 1, 0, then you'd be like, well, I probably need to check more. Because like, is it pointing more up or is it pointing more right? If it was pointing more up, it's probably going to be counterclockwise. If it's pointing more right, it's probably going to be clockwise. All right, I should let you go.